well. We can just
quiet down a little bit and get to your seats. We're going to get started. Thank you all for coming to this year's 2025 STSCI Spring Symposium, Inter+Stellar. My name is Elizabeth Tarantino, and I'm the chair and organizer of the symposium. Before I get started with some logistics and an overview of the symposium, we're going to have a lovely introduction from STSCI Director Jen. So Jen, you can take it away.
Thanks a lot, Elizabeth. Welcome everyone to the 2025 STSCI Spring Symposium, Inter+Stellar, Harnessing the Intersection Between Stars and the Interstellar Medium. Thank you all for attending, both here in person and online. Thank you to our organizing committees. It's really just fantastic to be able to meet and talk about science for a little bit here. We should not take that for granted. So this workshop in particular is special. The past decade of research has shown that the most exciting advances come from considering both stars and the interstellar medium in unison. And so this week, we're going to focus on how modern high-resolution observations, especially of the nearby universe, allow us to harness stars and the ISM together to advance our understanding of both. The main themes, as you know, are going to be using stars to better understand the ISM, using the ISM to better understand stars, and understanding stars and the ISM together. And so the science presented here not only focuses on this topic, but also showcases the work of a wide range of facilities. Of course, here at STSCI, we like to talk about Hubble and Webb, but that's not the only facilities that have really been pushing this field forward. You'll hear about science from Gaia, ALMA, the VLT, Sloan, Chandra, GMCT, and Meerkat, among others. And much of the science here is made possible by the fantastic spatial resolution afforded by these facilities that's changing our ability to use data and simulations together. One quote from early JWST releases is, "Finally, the data are starting to look like our simulations." I don't work in this field. I work on galaxy simulations and galaxy mergers, and likewise, it's pretty amazing to see that revolution. The fact that Hubble and Webb are multi-instrument, general-purpose observatories is especially relevant to this symposium, as both telescopes are extremely well-suited to studying the stars and the ISM. And the ways in which those two telescopes work together is very synergistic. We think about that a lot here. Hubble is great for studying bright young stars and the emission lines from the ISM that are energized by star formation. And Hubble's unique capabilities in particular are invaluable for measuring extinction and metal line absorption. And I'll remind people, Hubble is not going to be superseded in this decade or perhaps later. JWST, as we all know, is lifting the veil on highly obscured stellar populations, providing a quantum leap in our ability to study the ISM through shock tracers, warm molecular gas, dust, and PA emission. The interdisciplinary nature of the symposium, combining stars and ISM together, helps connect to our mission here at Space Telescope, which is to run not just Hubble and Webb, but thinking forward to the future with Roman and habitable worlds. And so thinking about that, I hope we'll hear about Roman's large field of view and how its exquisite resolution will revolutionize studies of nearby stellar populations. We're going to have access in the future to the far infrared with missions like Prima. And then we're thinking a lot here about the Habitable Worlds Observatory and how this Ultra Hubble with UV and optical capabilities will transform science into the 2030s and 40s. So again, I want to say thank you to our organizing committees, both locally and the science organizing committees, all of our speakers, the SOC chairs, Elizabeth, Christopher, and Josh. And thanks to NASA for allowing us to have this symposium this week. All right, so I'm going to hand it over now to Elizabeth.
Thank you, Jen, so much for that lovely introduction. It was awesome. And thank you all again for traveling near and far to come here. I'm so excited. I'll just introduce myself again. I'm Elizabeth Tarantino. I also go by Liz, and I'm the chair and organizer of Inter+Stellar. I just want to give you all a heads up to not hesitate to reach out to me or my wonderful co-chairs, Chris and Josh. If you have any issues throughout the weekend, we're here to help you out. So Jen already talked about our concept for the conference a little bit, but I want to go into that a bit more. This conference was developed by recognizing that stars and the ISM have become increasingly interdisciplinary. It's now common practice to study both stars and the interstellar medium together, as each can serve as a powerful tool to better understand the other. Thus, Inter+Stellar was created to highlight these synergies and interactions between the stars and the ISM. This is especially apparent from this word cloud that we made that includes the almost 100 abstracts that will be presented this week through talks and posters. And as you can see, stellar, stars, star, and gas, dust, ISM, and interstellar are all very well and equally represented words that kept on appearing throughout the abstracts that you'll hear this week. Now, our conference schedule, because it was so interdisciplinary, was a bit difficult to classify. You all put in a ton of really creative and awesome abstracts in. So instead of focusing on discrete sessions, we rather instead focused on making a conference flow where sessions will nicely transition from one to another. So today we're going to start with 3D pictures of the ISM and stars, especially focusing on results coming from the Gaia Space Telescope. And then we'll move on to absorption, extinction, and attenuation of starlight more generally. Tomorrow, we're going to be talking about the dynamic ISM, specifically high-resolution observations of both stars and the ISM locally. And then we'll transition into stellar deaths. This includes supernovae and evolved stars and how stars can enrich the surrounding interstellar medium. On Wednesday, we'll be talking about chemical enrichment more generally on the scale of galaxies. And then we'll transition into feedback and how stars can impact their immediate environment through feedback processes. Then on Thursday, we'll zoom out a bit more to stars and their environment more generally, and then focus instead on star clusters and their formation. Then on Friday, we have protostar and YSO Friday. So that will be fun, and that's going to be zooming in on the physics of early star formation. So all of our talks will be 13 minutes plus 5 minutes for questions. So we're really excited to hear about all of your awesome ideas, and don't be afraid to ask a lot of questions, both in the coffee hours in between and in the talks afterwards. In addition to our scientific program, we also have a lot of fun social activities planned for this week. So today at the STSCI cafeteria, we're going to have our conference welcome reception. Then tomorrow, we'll have a Baltimore Orioles baseball game. I'm very excited for this. Go O's. Just to know that transport's not provided, and we are also keeping a close eye on the weather. So I'll give you guys an update on that once we know what's going on tomorrow. On Wednesday, we have 2 fun events. So right after talks, we'll have the STSCI happy hour. This is also called STAS and is a long-running tradition at Space Telescope since the 80s. And then later in the evening, we'll have an Astronomy on Tap talk that will feature presenters from this conference. They'll be giving a general public talk at a local brewery. So come by to support your colleagues. We're going to have awesome talks from Timothy Davis, Sundar Srinivasan, and Thomas Williams. Then on Thursday, we'll have our unbanquet at our house. Now we call it an unbanquet because it's not going to be a traditional sit-down tablecloth kind of affair. Our house is a local Baltimore favorite, and it's a food hall that has 10 different food vendors that serve a variety of different cuisines. So we've rented out a space at our house, so it will be a nice opportunity for you to mingle with your colleagues before the conference ends. And just to know that our house is a nice 20-minute walk from STSCI through Johns Hopkins campus. As mentioned earlier, we are excited for this symposium to be interactive and interdisciplinary. And one of the ways that we're going to be doing this is through our discussion sessions Tuesday, Wednesday, and Thursday. So we've set up a whiteboard in the cafeteria, and we will be soliciting your questions and your discussion ideas. So all you need to do is, if you have a question or an idea based off a talk or a conversation with your colleague, you can put that up on the whiteboard. And if you're interested in leading that discussion, you can initial your idea. We will then be voting on your favorites. So feel free to just put a tally mark on the discussion ideas that you find most interesting. And then the top 3 or 4 topics will be selected for discussion Tuesday, Wednesday, and Thursday afternoon. We will break into 3 groups, 3 breakout rooms, one in the auditorium here, one in the cafe, and then one in the cafe conference room. Adam Smersina, I don't know where Adam wave. There he is. Adam Smersina is the LOC member that will help facilitate the discussion sessions, so feel free to come to him if you have any questions. We also have an exciting Friday afternoon hack day. So this will give you an opportunity to collaborate on new ideas inspired by conference discussions. Hacks can be a variety of projects, whether it's a new code that you're interested in building, a white paper based off of discussions, or perhaps a telescope proposal idea that you would like to develop. We'll be collecting Hack Day ideas through that QR code link there. This is also given on the website, so you can find it there. So you can submit your Hack Day ideas there throughout the week. We will also have a special Thursday discussion session where people can give their Hack Day pitches. So this is where they'll explain the idea that they would like to do, and then can have volunteers from the conference if people would like to help out with whatever their hack idea is. There's also a series of pre-planned hacks that involve some data analysis tools that are going to be run by some conference attendees. So if you're interested in getting involved with any of these, feel free to reach out to the organizers. They will also be on a running list of all the Hack Day ideas that we have that you'll be able to find on the website. And a shout out to Eric Tullerud and Christina Lindberg. These are our Hack Day coordinators. So these are your point people if you have any detailed questions about the Hack Day. Now, before we get into talks, I just want to go over some quick logistics. So first, the Wi-Fi information. It is there. I will leave it up for a second. Second, the auditorium. So above your heads, you may see these little microphone square things. So these are our ceiling microphones, which make it so we don't have to pass around microphones during Q&A session. They can just record all the questions that we have in the auditorium. This is awesome because it means less passing around, but it also means that they will record everything. So make sure that you're a little bit quiet during the Q&A, or some of our online friends may be able to hear your conversations. And lastly, we also have a Slack workspace for the conference. That's a QR code where you can join it. There's also a link to join in one of the emails that we sent you, so you can find it there as well. This will help coordination, especially transportation to things like the baseball game. So feel free to join that as well. Now, lastly, I just want to give a lot of thank yous to everyone that made this conference happen. So a huge thank you to the scientific organizing committee who really helped shape the conference and selected abstracts for all the great talks and posters we're going to have. The folks in bold are the ones that could make it in person, just as a heads up. And I also want to give a huge, huge shout out to my co-chairs, Chris and Josh. It's been a lot of fun planning this with you guys, and you've really, really done so much work. So thank you so much. Next, I'd like to thank the local organizing committee. You can see here, they have been so helpful in organizing tasks from the baseball game to the hack day. And I'd also like to emphasize my thanks to the STSCI events planning group, and especially Shemaya Smith, who has been absolutely integral to every aspect of symposium planning. So thank you so much, the events planning group. And then most importantly, thank you, the conference attendees. Your ideas, talks, posters, and discussions are truly what will shape this symposium, and I'm so excited to hear what you all have to say. Thank you all so much. Do I have any questions about logistics, about the conference? Okay, awesome. If you come up with any, feel free to find me. I'll be here all week. With that, I think we can start with our first talk. So Josh will be sharing this session.
Sure. All right. Thanks for getting us going, Liz, and thanks for doing the lion's share of the work putting this conference together. This has been truly extraordinary in running this thing. Are you okay?
Yes.
All right, so it's time recording. We'll start.
Okay.
And we're going to start with an invited talk from Greg Green. Why don't you take it away, Greg?
Great. Thank you. Thanks for organizing the conference. And today I'm going to talk to you about variation of the dust extinction curve and what we've been doing with Gaia to really, I think, give us a much fuller picture of how the extinction curve varies throughout the Milky Way. I'm also going to give a small overview of three-dimensional dust mapping just to start us off, and then go into the new work with Gaia. So at a normal conference or a different conference, I would begin by saying, what is dust? And I'd tell you about, its small particles up to about 1 micron in size. And I'd try to convince you that dust is important. And I would point out all the different things that dust is important to. And I'll just give a little rundown, star formation, planet formation, CMB foregrounds, stellar population synthesis, large-scale structure, chemistry of the ISM. But I'm sure this is all going to be very thoroughly covered in this conference. So I'll assume that everyone here is on the same page with all that. So I'm assuming that you guys think that dust mapping is an important question. And there are basically two ways to map dust in our galaxy. One is through the emission of dust. And so what we have is a really beautiful picture here of dust far infrared emission from the Planck satellite. And so you can see this traces a huge amount of very detailed structure. The nice thing about this is it's high signal to noise, it's high resolution. The downside is that you can't tell the distance of the dust because intensity doesn't carry any distance information. You can only tell at every sightline the integrated amount of dust. A second way of trying to map the dust is by using the dust extinction. So looking at the light of background stars and trying to use that information to determine where the dust is. And there are basically two ways that we can do this with extinction. One is by looking at the colors of stars. And so in this zoom in, which by the way comes from the DCAPS survey, a galactic plane survey with DCAM, you can see that the colors of stars behind the dust become redder. But you can also see that the number counts of stars change. And so if you see a region without any observed stars, that is an indication that there's a lot of dust there. And actually, the very first attempts at three-dimensional dust mapping all the way back in the 1920s used this star count information. But all modern ways of mapping three-dimensional dust basically only use the colors of stars. And maybe there's some sort of opportunity there to actually combine these two types of information. The math is clear about how you do it, but the implementation is actually very difficult. So this is a very classic map of dust from Schlegel, Finkbeiner, and Davis, 1998. And this is using far infrared emission. And so this has been a very standard work, especially in extragalactic astronomy, for removing the effects of dust extinction for now almost 3 decades. As I said before, though, the downside of this is that we don't know where the dust is in 3D in this map. If we want to know where the dust is in 3D, we really have to use stars. And so let's say that this is the sun, and we observe a large number of stars surrounding us in the Milky Way. And then if we put dust clouds here, the stars that are behind an individual dust cloud will be redder. And so you can see along different sight lines, we kind of have like a shadow of every single dust cloud where the stars appear redder. And then if we select just one sight line, we can then trace, as a function of distance, just by looking at the colors of stars, the amount of dust. And so this is basically how all three-dimensional dust mapping techniques work. They just look at the colors of stars, and the stars behind the dust along each sight line will be redder. The stars in front of the dust will be bluer. The thing that makes this difficult, though, is that not all stars have the same intrinsic color. And so if you actually take into account the fact that stars have different temperatures, stars behind the dust cloud, on average, will look redder, but you'll still have very, very hot stars that will look kind of blue. And you'll have also things like M dwarfs and so on in front of the dust cloud that will look red. And so you have to actually do a full Bayesian analysis of this to determine jointly the properties of the stars and the location of the dust and solve that entire problem. The way that this works along one sight line is that we pick the sight line. So we generally pick the location that we're interested in. And then we're going to plot distance versus extinction. And for every star, we actually infer all of its properties, including its temperature, surface gravity, metallicity. But we also determine its distance and extinction. And so we have a whole Bayesian model of that. And so then this is the probability cloud for one star in distance and extinction. And we then repeat that for different stars along the line of sight. And every star gives you a different constraint. And you can already then see sort of that there's a dust cloud at this distance in this sight line. And then we look for a curve that is, let's say, the maximum probability curve of how the dust could be increasing with distance. And if we're doing this in a Bayesian way, we actually determine a set of curves that are drawn from some probability density function on where the dust could be. And so we actually end up with, on every single sight line, this sort of set of curves. And if you repeat this then for several million sight lines along the sky, you get a three-dimensional map like this. So this is showing you the 2019 base star map, all the dust within 0.5 kiloparsecs. And so you can see there's a huge amount of very detailed structure here. And we can step out in distance and see all these beautiful clouds at different distances. And so this has been a very successful method, I think, at determining the three-dimensional structure of dust in the Milky Way. We can also make beautiful videos about this. So this is taking a virtual camera, orbiting around the sun, and looking towards the galactic anticenter. And you can see here the Orion A and B. You can see Perseus is down here, California is here, Taurus is here, and then all the clouds in the Milky Way midplane. If we look at a top-down view of these maps, what you often see is this sort of pencil beam effect, where the clouds appear to be oriented towards the sun. And obviously that is not really that's not consistent with our view of the universe. We're not in some special place. These clouds should not be just directed towards us. And the actual reason for this is that it's very easy to determine the angular location of a cloud, but very difficult to determine its distance. And so the distance resolution is always much, much lower in these maps than the angular resolution, which leads to this sort of pencil beam effect where the clouds are smeared along the line of sight. So there have been various attempts to improve this through various regularization schemes. And I think to date, the best attempt has been, or the best approach to doing this has been taken by Gordy and Edenhofer et al. And this is their latest map. And you can see here that within 1.25 kiloparsecs, by applying a spatial prior that says that the dust should be spatially coherent across different sight lines, they're actually able to recover a dust map that looks much more plausible in terms of its distance structure. And if we zoom in on this map, you can see all this very beautiful structure here. And basically what they're doing is they're assuming that the dust clouds have some spatial coherence and don't have any preferential direction. And so you can see that they've really done, I think, a really incredible job at getting this local dust in 3D. So all of these maps so far have assumed that the dust extinction curve is universal. That is that all the dust everywhere in the galaxy is all the same. It doesn't vary chemically or in terms of its grain size properties. And so what you get is, as a function of wavelength, the normalized extinction. So just if you take the extinction and normalize it by the extinction at some standard wavelength to just get the shape of this curve, that it's universal everywhere. And so we know that's not the case. And the variation in the extinction curve is typically parameterized by this variable called RV, which is based on extinction in two optical bands, B and V band. And this is something like the inverse slope of the extinction. So a lower RV means a steeper slope, a higher RV means a flatter extinction curve. Then there are other features that we know about, like the 2175 angstrom feature in the UV, that's also known to vary, and 3.4 micron feature. And both of these are carbonaceous features, and they're known to vary across the sky. And so there's a lot of variation that has not been captured in these three-dimensional dust maps yet. So I'll give you a little cartoon explanation of what the origin of RV is. And so a typical explanation for RV variation is that the grain size distribution is changing. So if we have wavelength versus extinction, that's this curve here. And then we have the sizes of our grains, and we have some population of grains of different sizes. If most of the grains are very small compared to the wavelengths that we're looking at, then we're in the Rayleigh scattering regime. And the extinction curve will be very steep with wavelength. And that corresponds to low RV. If we make all these grains really large compared to, let's say, the optical wavelengths that we're observing at, then the extinction doesn't really depend on wavelength, and we get a very flat extinction curve, which corresponds to high RV. So typically, small grains mean low RV, and large grains mean high RV. And this is sort of the typical picture that we have of RV variation. So the next part of the talk, I'm going to show you how we went from just having dust density to actually across the entire sky having dust RV. And that's what I'll try to explain in the next few minutes. So almost all of the dust maps that I'm showing you, or that I've shown you so far, have been based on photometric surveys like Pan-STARRS 1. And these surveys typically have a few very broad filters, let's say like something like 5 filters spanning the optical range. So they give you extremely rough spectral information about every star. Over the last decade, we've also had Gaia parallaxes, and those give you a distance or more detailed distance information about a lot of the stars. But what I think is really revolutionizing 3D dust mapping right now is the availability of large numbers of low-resolution spectra across the entire sky. So I'm actually cheating here, and this is actually a picture from Euclid. But the idea is the same. The idea is that in every location in the sky, you get a slitless spectrum. So you get a spectrum of everything that you're looking at. And by disentangling these various spectra, which are possibly overlapping, you get a low-resolution spectrum of every single star. And so this is what a Gaia spectrum looks like. We have actually two. One is a blue spectrum, one is a red spectrum. And you get these smudges for every single object. And you get something like an R of 50 to 150 spectrum for every single star. And so Gaia has taken, so far, 220 million of these across the entire sky. And for short, because we have two of the BP and RP spectra, we just call them XP spectra. So how are we going to extract our astrophysical information about every star from these very low resolution spectra? So one way to go about this is to cross-match with some high-resolution survey from the ground, like LaMost, and that gives us, for some very small subset, like 1% of the stars, information about their effective temperature, metallicity, and surface gravity. And then we could do some sort of machine learning thing where we would just learn a direct model that goes from these spectra to the stellar type using some sort of supervised learning technique. But in my group, we wanted to actually do something a little bit more principled. So we actually learned a forward model that goes the opposite direction from the spectral parameters to the spectra. And then what we do is we're going to use Bayesian inference to actually infer the properties of all the stars using our forward model. So if we train our model, our forward model, on 2.4 million stars, we get these models of how stellar spectra behave with effective temperature and also with metallicity and surface gravity. And you can see that there's actually a lot of real features here. For example, we can see that the Balmer and the Paschen lines are behaving in the way that we would expect with temperature. They're getting stronger at higher temperatures, for example. And also that the metal lines are also behaving the way that we expect with temperature and with metallicity and so on. So these models actually contain real information about stellar spectra. We also learn the extinction curve and how it varies with RV. And so just to orient you, this is low RV, which means small grains, high RV, which generally means larger grains. And we've traced as RV changes, how does the detailed optical extinction curve change? And you may notice these various bumps and wiggles. And the question is whether or not these bumps and wiggles are true. And I'll get back to that later. So now we have this forward model, and we have all these Gaia spectra. So we'd like to infer the parameters of both the stars and the dust in the foreground. And so we're going to use XP spectra, but we're going to augment them by near-infrared photometry and Gaia parallaxes. And we're going to infer the parameters of 220 million stars. So we do that. In this part, we're not actually using high-resolution spectra from the ground, because we don't assume that we have them for all 220 million stars. So if we remove stars with bad chi-squared, per degree of freedom, or low extinction, we end up with 130 million RV measurements from XP across the entire sky. And this is what that looks like. So the central panel here is the midplane of the Milky Way, and it's showing you RV. So blue means high RV, or large grains. Red means low RV, or small grains. And then I've zoomed in on various clouds just to show you that there's actually a lot of detailed structure here. For example, if we look at Orion, in general, the outskirts of Orion seem to have low RV, but if you then zoom in, for example, on the Orion Nebula, suddenly you have all these stars with very high RV. So there's both large-scale structure and small-scale structure in this map. One thing that we noticed that was surprising to us was that in a lot of clouds, at very low density, in the outskirts of these clouds, RV is actually decreasing with density, and then it only turns around and starts increasing with density in the very dense parts of the cloud. And typically, the picture previously was that RV should generally increase with density, because in denser environments, you have larger grains which are forming. And so that should cause RV to increase. But instead, in many, many different clouds, we see this typical U-shaped trend where RV first decreases and then increases. We also can map RV in the galactic plane. So what I'm showing you here first is contours of the dust density around the sun. The galactic center would be off to the right, somewhere over here. And then we can plot the RV in the galactic plane. And then if you overplot the OB stars, you actually can notice that regions with a large density of OB stars tend to have higher RV. So that's another interesting trend that we noticed in the data. And then finally, we also have RV in the Magellanic Clouds, the small Magellanic Cloud, the large Magellanic Cloud. And also in the LMC, we noticed the same thing, that these star-forming regions tend to have higher RV. So I think for the first time, thanks to Gaia and these low-resolution spectra, we can actually see dust properties throughout the Milky Way in 3 dimensions. And we have two surprising results. One is this U-shaped relationship between density and RV. And the second is this apparent correlation between star formation or maybe UV radiation and high RV. So I'd like to just tease one thing here, which is that we think that there might be a connection between polycyclic aromatic hydrocarbons, or PAHs, and this U-shaped relationship that we're seeing between density and RV. So this is described in a paper by a student of mine who's here, Xiangyu Zhang, and Brandon Hensley and myself, which just came out. And Xiangyu also has a poster that you should go look at, which explains what we think the connection is between PAHs and RV. So in the last part of this talk, I'd like to talk about whether or not there's information beyond RV in these spectra. So far I've only talked about RV, which is the sort of overall slope of the extinction curve, but there should be much more going on chemically in the ISM than just this 1 degree of freedom. And that should be something that you can see actually in the extinction curves. So what we do is we actually calculate these empirical extinction curves for several million stars that we have in our catalog. And the way that we do this is that we have an observed spectrum for every star. And then we fit our forward model to that spectrum, which takes into account extinction. And so, for example, this is our best fit unreddened unreddened spectrum of this star. And these are the parameters you can see that we fit. And the difference between the unreddened spectrum of the star and the observed spectrum of the star is the extinction. And so we get an empirical extinction curve for every single star with some uncertainty and actually a covariance matrix telling you how every wavelength is correlated with every other wavelength. And just to compare, this is our best fitting 1 degree of freedom, so RV dependent extinction curve. And you can see that if I take the difference between these two things, there are some bumps and wiggles that are not contained in our 1 degree of freedom extinction curve that only depends on RV. So the question is whether these bumps and wiggles are true, whether they're real or just some artifact of the data. So what we did is we took all of our extinction curves and we normalized them in some standard way and then took out the average extinction curve. So then this is the variation around the average. And we did some component decomposition of these extinction curves. So for every star, this is the thing on the right, which is just the variation away from the average extinction curve. And we did a component decomposition where every star is going to be some set of coefficients times some set of basis vectors. So these basis vectors are just, as a function of wavelength, some shape. And those are universal for all the stars. And we'll have 16 of them. And then for every star, we'll have 16 components that will say what its extinction curve is. So this is a form of dimensional reduction very similar to PCA, except that the one special thing we're doing here is we're taking into account the full uncertainty and the covariant uncertainty of every extinction curve. So it's basically like a Bayesian PCA. And what we get is these extinction curve components that have some shape and wavelength. So this is showing you the first component of variation, so the dominant mode of variation and how it varies with wavelength. And you can see this just makes extinction less at short wavelengths and more at long wavelengths. So this is just RV. And this is the map of that component on the sky. But then we have these higher order components, which do more complicated things. So these are components which are orthogonal to RV variation. And they have various broad and sharp features in them. And this is this one component's imprint across the sky. And we actually have 16 of these, but I'm just showing you the first 4. So this is the component 2, this is 0 index, so it's component 2 and component 3, and then their variations across the sky. So what we're getting is both spectral information and spatial information about these components. And you can see that there's a lot of detailed variation. And if we zoom in on these, they actually look quite dust-like, I would say. So you see these sort of filamentary and cloud-like structures in these lowest 4 components. If you go to the higher order components, they start looking like Gaia residuals, which typically look like these arcs across the sky and checkerboard patterns. So we believe that the lowest 4 orders of this expansion are actually physical variation of the extinction curve, and that the higher orders contain mostly information about Gaia systematics. We also found a new broad feature at 850 nanometers, or actually centered at 848 nanometers in our data, And we can actually map this across the sky. And we also confirmed a previously known feature at 770 nanometers, approximately, that was found by mice Apollonese in 2021. And we can actually map both of these features. So this is a 770 nanometer feature and its strength across the Milky Way midplane. And this is the 850 nanometer feature and its strength. And these are very similar to each other, but not actually quite the same. You can see, for example, in some regions, the 850 nanometer feature is very strong, but the 770 nanometer feature is not. So they're correlated, but not exactly. All these features are of unknown origin. So we don't know what the chemical origin of these features is, but there's something in the ISM which is changing to make these features. One other thing I'd like to tease is a paper that Andrew Sgr A and I are working on right now, which is correlating these with diffuse interstellar bands, DIBs, and it appears that there is a correlation between these features. So what I'm showing here in these two rows is how RV correlates with the DIBs. So as you change RV, this is how the DIB features change. So you can see that the 15272 DIB is getting stronger, and actually most of the DIBs are getting stronger with RV. And then this is showing you with the second higher order component of extinction how other DIBs are changing. And so some of the DIBs do correspond to that or do change with that feature, some of them don't. And we're tracing that for a whole set of DIBs that you can see in apogee and in Gaia RVS spectra. So I think that with Gaia XP, we're getting a new frontier in three-dimensional dust mapping, which is mapping RV and even variation in the dust extinction curve beyond RV. And this has really been made possible by having so many low-resolution spectra across the entire sky. And this is something that I think that we should really think about being able to expand to other wavelength ranges. Right now we've done this in the optical, but there must be a lot in the infrared and in the UV. And the really surprising thing to me about this is that we don't really know what causes all of this variation that we're seeing. So with that, I'd like to open up to questions.
Thank you so much, Greg. From the audience. Yes, first of all, very interesting talk. Thank you for that. When you're looking at the RV and how that varies with the intensity where you recover the U curve,
yes.
Do you also probe whether you're tracing different ISM conditions when you're separating the gas, whether it's star forming or not, or is it all, you only look at the density variation across the sky?
So we've been looking with this U-shaped curve. We looked at two things. One is just the density, and one is where the O stars are. Okay. And so we think there's some relation between them. And Xiangyu's poster will explain sort of what our thinking is about the physical origin of that. But we think it has to do with two things. One, we think it has a lot to do with the PAHs and both growth and destruction of PAHs in these environments. Yeah.
Thanks a lot for a really fantastic talk. This data is amazing. Maybe I should have been able to read off one of your figures, but just for the sake of asking, do you see any, what are the characteristic spatial scales associated with these fluctuations in the RV that you think are physical?
There were actually variations on many different scales.
Yeah, sure. But there were a few that seemed to kind of poke out my eye.
So you can see that these clouds tend to have lower RV. So if you've memorized the map of dust clouds in your mind, this is, for example, the Aquila Rift. And you can see that in general, these intermediate density regions that you can see here have lower RV. So we think it has to do with the local density of the ISM and also with the amount of UV radiation, probably. That's our thinking right now. There are some very local environments like the Orion Nebula where the chemistry might be quite different, which have very high RV. So it's hard to say that there's one spatial scale because the ISM is sort of fractal in nature.
I have one question, Greg. When you, in part of your talk, you use Gaia data and the extinction to reconstruct the 3D. ASM, and then you also study the dust. And it's not clear to me how self-consistent this is and how important it is to account for the RV variations, extinction curve variation, to properly rebuild the 3D itself.
Yeah, so I think that one thing that should be done is all of these three-dimensional maps, like, to go back to this, these three-dimensional maps were created assuming that the dust is all universally the same type of dust, and they should all be redone with an RV-dependent extinction curve. So it should be done, I mean, it will actually change this. The main thing that I think will change is the distance to some of the clouds will be distorted a little bit by RV variations.
And is it challenging to redo this, or?
Conceptually, we know how to do it. It's just the person time to actually do it. Yeah.
Yeah. So traditionally, we always do RV with sizes. Do we do anything about chem composition?
Yeah, so that's what we think is that actually chemical composition, the pHs, basically the pHs have this, I have a little graphic of the extinction curve here. One of the leading theories for the composition, or for the reason for this 2175 angstrom feature, is pHs. And if you increase the strength of this feature, you actually increase the slope of the optical extinction, because there's a long tail to this feature. And so by changing the amount of PAHs locally, you can actually change RV as well. So it's not all grain size. That's the typical picture. But we think that actually, if you just double the amount of PAHs, which is very possible given the carbon budget, you can actually change RV by something like 1 sigma in terms of the variation inside the Milky Way.
And are you using any polarization data?
Not yet, but we're interested in getting polarization data.
Rather than just looking for differences in spatial scale, have you or others tried to decompose it into filaments versus shell-like structures?
So I think that there are people who are working on decompositions of the ISM into different types of structures like that. I think, for example, Theo O'Neill has done some work on that, and yeah,
Giving a talk.
It's giving a talk. Yeah, this session. Yeah. So yeah, just wait till that talk.
Do you have anything from online?
Concerning competition, you mentioned about PHs, but how about graphite or amorphous carbon? Do they contribute to RV variation or not?
If they contribute to the 2175 angstrom feature, and depending on how wide that feature is, they could. So basically, anything which gives you a wide 2175 angstrom feature that goes into the optical will change RV. Yeah.
Hi. So I kind of would have expected that with the low resolution spectroscopy, you hit degeneracies between the temperature and RV. Could you just talk a little bit about the challenges involved in?
Yeah. So for me, coming from the photometric, all my early work was photometric. It's a big step, towards you get much smaller uncertainties. So our typical uncertainty, for example, in extinction, or say B minus V, is something like 0.03 magnitudes per star. And then there's some corresponding temperature variation, and they're very covariant with each other. And then we do this over many, many different stars, and so that's how we get the errors down. But there is still some covariance there. So we actually trace the covariance, and in our papers, we always, in our catalogs, we always report the covariance as well. But 0.03 magnitudes in B minus V is kind of what you should have in your mind.
Do you think that you get much more of a gain by going to higher resolution, or do you think it's the high numbers that's more important?
So I think the real thing, or the really important thing that Gaia has added is full sky coverage and having so many spectra. Yeah. So you do well enough to actually constrain RV fairly, to within much less than the variation inside the Milky Way, and you get it across the entire sky. Versus high resolution spectra for small numbers of stars, they're obviously complementary to each other, because you can learn other things that you can't learn from low resolution spectra from these high resolution spectra. But I think that we didn't previously have this regime of just having the entire sky covered with low resolution spectra. So what it's given us is this 3D picture, and you can't do that with high resolution spectra.
And actually, let me jump in with that follow-up question, which is the stability of space. Does that help a lot here? You know, if we talk about something like DESI or something like SDSS5, which will, you know, have plenty of spectrum. You know, do we reach a floor where the systematics sort of drive things and it becomes very hard to deal with? Or is that really not so much of a concern? It's really just numbers?
Yeah, it's a good question. And I think that might really be relevant to the beyond RV features where, yeah, so at some point we can see in our data, for example, the Gaia features take over.
Yeah.
So if I go, you know, in these features, suddenly the Gaia systematics are taking over. So the question is, at what point would you reach that floor with the high resolution spectra from the ground?
Exactly.
I don't know.
Yeah, okay, great. All right, let's thank our speaker again. Excellent start to our conference.
Yeah, sure. So what should I do here?
You gotta find your talk.
Yes. Jump. Yeah. Okay. Yes.
How's that look?
Yes.
All right, you'll have 13. You'll have 13 minutes.
Yes.
All right, take it away.
Yeah, so my name is Sihao Cheng. I'm a postdoc from Institute of Advanced Study. The community of interstellar medium is really new to me. I worked a lot on other fields, cosmology and also dynamics about the solar system and the Milky Way. But I'm really glad that I have this opportunity to tell you something new, both to me and to you, I believe. I realized that my talk is really unique in this session because all the others are about map of ISM, but only my talk is about a map of stars. And also the others are for 3D maps, but I'm going to show you a higher dimension map. So that's what you can get good about stars, because the star also have velocities, not just like a thermalized distribution. Right, so I'm going to show you the result first and then explain. I think there are some really interesting new discovery here. So this is an illustration of the Milky Way disk, right? And with this new mapping skill, I'm going to show you, this is basically a stellar number density map. You see that there are sharp structures and with very high density contrast, which are unseen before. What's more interesting and related to the ISM is that if you color code it with metallicity, you start to see stripes and very sharp transition. So the background here, right, when we talk about metallicity distribution in the disk galaxy, you would imagine it's a smooth like drop from the center to the outer part, right? No one really have, I mean, I suppose people consider these kind of mapping, but what you get is just a smooth distribution. So I'm going to explain how you can get this sharp structure with this map. Right, so the idea is basically using the velocity information of stars, again, thanks to Gaia. So this idea is quite new, right? We have the velocity distribution of the solar neighborhood long ago, probably dating back 100 years ago. People talk about stellar streams in the solar neighborhood and moving groups. And this is 20 years, 30 years. What is it? 30 years almost, right, ago, we have these Hipparcos data. So the feeling you get, right, it's basically some moving groups, some blobs of things. And this is what you have in Gaia. So I think not really improving a lot. It's basically just a mass of blobs. So I'm going to show you that if you have a better mapping skill, you can see clearer the structure. So the key here is that even if we only talk about the in-plane motion of the disk, there are x and y two-dimensional spatial and also two velocity dimensions. So it's a 4D space. And the question is, if there are structures in this space, how do you visualize it? So for a while, people do velocity and marginalize over space. And then recently, people realized with the power of Gaia, it makes more sense to do a variable transformation to make it dynamically more meaningful, which is to decompose the motion of orbits into like a guiding center motion and the epicycle motion, a large circle and a small circle. On top of that, you might recall something from your dynamics course. And then you can have the amplitude of this circular motion and the phase of this circular motion, right? So basically, you can do a variable transformation from xy, vy into two amplitude of circle and two phase of circle. That's called action angle. Right, so if you do this, but still this is a 4D space. So for a while, people thought, okay, I think it's well mixed in angle, so I only plot action. That's what you get. This is probably right after a second Gaia data release 5 years ago. People get something like this. You see structures, they're kind of vertical with a slope, but it's kind of 10%, 20% structure in contrast in number density, right? You might imagine this is just a small effect. But what we've done is that in this 4D space, what about if you do 2D slices instead of doing a marginalization? So that's a very natural idea, right? When you have a 3D structure, if you want to have the full idea of it, you need to do slicing instead of only looking at it from one direction. So if you do that, it's kind of magical. You start to see a lot of structures there. I'm going to show it again. These are slices when you change one of the other parameters. You have 4 parameters here showing you 2 parameters. There are 2 left. And if you change one of the other, you see how these structures come and go. So first, it becomes very sharp and with very high density contrast, right? The density contrast here is order of unity instead of like 10%. And also it moves. So these are basically dynamical fingerprints of the Milky Way potential, right? And if I just show you with a static image, you see at 4 different angles how different these structures are. And by the way, one other new thing I've done is that I correct for selection effects, caused by the distance of stars and also dust extinction. If you don't do that, you don't have these full, clear, uniform mapping of the phase space. You get a very biased view of this phase space. It's almost certainly related to resonance, like the bar, maybe rotational Lindblad resonance. But the interesting thing is we don't fully understand it yet. So you can see there are some similarity, right, of these structures, the slope especially, to the observed structures. But the number density, like from naive, not naive, this is a kind of simple model of the bar evolution, like a slowing down bar. It creates overdensity underdensity pairs, but that's not what you see in the observation. So it's kind of very interesting. There's something more than the simplest idea. And also I talked about it already, right? One is you can change the view. Instead of doing the vertical slices, you do horizontal slices. here the coordinate are guiding center position. So that's like, remember, you do the decomposition of motion, you assume the star is, you have a guiding center, which is perfect circular motion. It represents the angular momentum of the star. And on top of that, you have the epicycle motion, which kind of represents the eccentricity of this orbit. So if you plot the map of guiding center, you see all these beautiful structures. It's just another view of the data, but this is similar to a map, really a map of the disk. And you see the metallicity structure. So that's the difference. If you plot a map of X and Y, you don't see this structure because it's mirrored out in velocity space. It's only when you plot a map of X guiding center and Y guiding center, you start to see these very sharp features. Right, so I think these structures are all new, and I'm preparing a paper, so I believe no one else knows this before. It's of course a very interesting dynamics problem, like about how to connect bar evolution, maybe slowing down, maybe some spiral arm interaction to explain this. But also I think it's very interesting to think about it in the ISM context, because all this metallicity, right, is determined from the metallicity of gas when they're born. Here I have an interactive tool to give you a better sense of how these slices look like, because again, this is a 4D space, so you can change one of the other parameter to see how this structure change. So you see that is quite consistent, right? If you change the amplitude of the epicycle motion, like the stripes there are almost always there. So maybe that's not related to the epicycle motion, but more related to the angular momentum. And on the other hand, you see here, right? These transitions seem to be also, the sharpness seem to also be a function of the epicycle motion. Right, so if you change angle, basically, you see another view of this. You see some structure come and go, probably that's Lindblad resonance. But you see the metallicity structure is always there. And you see it's not monotonic, right? For example, here, you can have like the flat here, and there's gap, and the metallicity go up again, and then drop. So it's a very different view. Right, so let me see, I think I have time. I just want to briefly mention to give you a sense of how important the selection effect correction is. Again, this is a map, like an illustration. And here I'm showing the 2D histogram of Gaia RV sample, where you have the full dynamic information. So how far would you guess Gaia RV sample can go from the sun based on this plot? Right, you might guess something like here, right? Because beyond that is basically darkness. So that will be something like 500 parsec. But if you correct for the selection effect, you see that actually you can go much farther, basically 4 kiloparsec away, until you hit the short noise limit. So this is really why I can have a much better uniform flat view of this phase space map than the previous works. Okay, to summarize, so I'm trying to make a good map of the phase space distribution of stars in the Milky Way disk. And because of these two techniques, one is slicing, one is correct for the selection effect, I found very sharp structures in this dynamical space. And what's interesting, I think, to you is that this structure is also related to a sharp metallicity structure. And what's more interesting, is also really puzzling to me, is that we can have a rough sense of, we can separate the star into two groups, young stars and old stars. And then you ask, what's the sharpness look like for young and old stars? You see that for young stars, it's even sharper. So then I would imagine if you go even younger, that will be the gas, right? So then the question is, what about the metallicity in gas? Is there a similar structure, like sharp transition in the gas phase already? And so that's the question. And what about in other galaxies if you see it in the Milky Way? That's all. Thank you.
Thank you so much. We have about 5 minutes for questions.
Why do you think that you're seeing this like sharp metallicity cliff in the Milky Way, and like where that conflict comes with observations in like other galaxies that are showing a more metallicity gradient?
Yeah, so I think the reason you see sharp thing here is because we have velocity, and this map is the guiding center map. It's not really the star position map. So for other galaxies, the problem for star observation is you don't see velocity. But I think it's possible to talk about the gas in other galaxies because there the velocity dispersion is much smaller. Right, so my understanding is that usually when you map metallicity of other galaxies, you only have like point sampling of a few like H2 region. And usually people believe it's a smooth function, so then you fit a whatever gradient or try to smoothly interpolate. But yeah, but if you really look, my question is, if you really look for something like this, can you really find it? Is it consistent with theta? Can it be consistent with theta?
Yeah. I would expect that the eccentricity would be smallest for the young stars.
Yes.
Correlate with metallicity. Is that what you're finding?
Yes. So it's a bit tricky. The most correlated thing is actually the vertical oscillation amplitude, because for the in-disk motion, it's influenced also by the resonance. So for example, here, the so-called eccentricity become high. It's not because only of scattering. It's also because of some resonance influence.
So I think there's been 2 papers that talk about this non-axisymmetric metallicity by Keith Hawkins and Eloisa Poggio, where they see this, but I think it's only in the young stellar population.
Mm-hmm.
You're saying these metallicity features are present in the older stellar populations as well?
Yes, but it's more smeared out. I think the reason probably is because some scattering, like of the orbit.
You know how old is? Is it a gigayear or?
I think more than a gigayear. So I only do the age separation based on the vertical action, the vertical oscillation amplitude of star orbit, which might introduce some selection effects or some, yeah, it's just a rough idea.
Great. So for correcting the selection effects all the way out to 4 kiloparsecs in the direction of the galactic center, are the dust maps good enough to do that?
I don't know, because here I'm doing the way I do selection correction is that I assume in the XY distribution is very smooth. So this is a fully data-driven correction. This
so
actually I haven't
dust
made
map that goes into this.
Right. I haven't made use of any dust map.
Any other questions from the audience? All right, let's take our speaker again. time.
Yeah, got it.
All right, Hannah Bish will be presenting on light cube. Take it away, Hannah.
Hi, everyone. I just want to say thanks again to Liz. I know how much work she's done to make this symposium great, so I'm really looking forward to what's in store this week. I'm Hannah Bish. I'm a postdoc here at the Institute, and I'm going to talk a little bit about a data product I've been working on. A bunch of my collaborators are here: Josh Peak, Claire Murray, Carl Gordon, Catherine Zucker. And so this is a 3D model of the UV interstellar radiation field, which we are calling light cube. And just so we're all starting on the same page, the interstellar radiation field is the electromagnetic radiation produced by stars and interstellar matter that permeates interstellar space. And it's really important to understand the ISRF because it is responsible for setting the properties of diffuse matter. So the physical, chemical, thermal, sometimes even dynamical properties of gas and dust in the ISM are largely set by the ISRF. And so the ISRF is a mix of components across different wavelengths, as you can see here. But I think the most important to model is the UV regime. And that's because not only is there a high density of UV photons, but these photons are both responsible for photoionizing the gas in the ISM, and they dominate the heating of the ISM. The UV is also hard to model because there's lots of spatial variation. So UV emission is driven mostly by young massive stars, which are clustered in space. So you can't just assume some smooth distribution. And then there's an additional layer of complexity because UV photons are preferentially scattered off of dust grains. And so you can see this here. On the left is a galaxy map of the UV sky, and you can see all of this diffuse UV emission where UV photons have been scattered off of dust clouds. And then on the right is an H1 map, and you can see how these neutral clouds roughly correspond to the regions where this UV light has been scattered. This was the poster cloud for our proposal, which we dubbed the shark, because it looks kind of like a shark there in the UV. So I'm definitely not the first person to try and model the UV ISRF. Lots of people have done this going back to the late 60s. So these are some of the more well-known models. You can see that they all drop off at the Lyman limit there, where neutral hydrogen absorbs strongly. And so these models were refined over time, but they're basically all doing the same thing, which is taking all of the UV flux in the sky and assuming some constant extinction to measure the ISRF at the sun. And you can make some additional simplifying assumptions to estimate the ISRF at different points in the Milky Way. But what we saw on this last slide with the shark is that the extinction and scattering is really important for where the UV photons end up, and it's certainly not constant across the sky. So if you want a really accurate map of the ISRF, these aren't the assumptions you necessarily want to be making. This is the best we could do for the past few decades. But we've had some advances in astronomy recently, which are going to allow us to update these models. So first, as we all know, Gaia has been an absolute revolution for stellar astrometry, and we now have really precise distances and coordinates for a lot of the sources of this UV emission. And we also have now really detailed 3D dust maps, which allow us to model how the UV light is scattered throughout the ISM. So knowing all of that, here's how we put light cube together. So we've got an all-sky UV catalog of stellar fluxes, which we cross-match with Gaia to get accurate positions. We've got a 3D dust map with 1 parsec resolution, and then we can combine these with a 3D radiative transfer code. We can trace the photons as they're emitted from the stars and move through the volume and are absorbed and scattered by the dust. And so then what we get out is this 3D map of the ISRF, which we're calling light cube. So I'll just briefly talk about these two components and then how we combine them together. So for the UV fluxes we need to build this model, we have turned to a survey that was conducted by the TD1 satellite in 1978. And if you're wondering why we're using a survey from 1978, it's because this is still the most recent catalog, all-sky catalog of UV fluxes that we have, believe it or not. So I had to run down some data quality issues with this catalog, and I got in touch with some old-timer UV experts who are familiar with this survey, who pointed out to me that the data was processed on punch cards fed into a mainframe in batches. So that's how old this is. But it fits the bill for what we need to build this model. It's an all-sky survey. It covers 31,000 sources in 4 UV bands. And then the second component is the dust. Greg gave a really nice description of dust models and dust maps and how challenging they are to make. So this is just a few of the 3D dust maps that have been published since 2019, and it's really amazing how much they've improved in just the last few years. This Like et al. 2020 map is one that we've used for a lot of our development and testing of the cube. And then this Edenhofer 2023 map will be the basis for our final release of Light Cube, which has similar resolution but covers a much larger volume. And then once we have our two components, we can combine them with a radiative transfer code. We're using this dirty 3D radiative transfer, which was developed by Carl Gordon here at the Institute. And so dirty uses this probabilistic understanding of how photons interact with dust clouds. Instead of a photon either being absorbed or scattered, it contributes to the weight of photons that are absorbed or scattered in a cell, and this continues for each interaction of the photon. So this makes the code a little bit more efficient, which is really important because this step is really the bottleneck in creating the cube. It's very computationally expensive to run a full radiative transfer. So I've spent a lot of the work that I've done on this project trying to make sure that we use the code as efficiently as we can and make good use of our computing resources. And so with that in mind, we've done things like run this radiative transfer at multiple resolutions, tried to optimize signal to noise by allocating photons efficiently within the cube. We've implemented repeating boundary conditions to account for radiation coming from stars outside the cube. And I spent quite a bit of time trying to work with this older data set and account for missing fluxes and think about incompleteness. So I want to show you a movie of our preliminary cube. This is a slice parallel to the midplane of the Milky Way. The sun is at the origin and galactic center is to the right. And then this animation will just step up through the midplane. And so you can see that some of the brightest star-forming regions really dominate the ISRF out to hundreds of parsecs. There's a lot of variation in the midplane. And then as you get to a couple hundred parsecs above the midplane, things start to look really smooth. You can also see some areas where light from the stars encounters a dense dust cloud and there are shadows cast, which is kind of cool. So I will leave this movie up at the end if you want to watch again. But now that we have our cube, we can compare the UV energy density in cells to the density of the dust there. And so one of the first things you can see here is that the UV energy density spans multiple orders of magnitude in the cube. So that's really underscoring this idea that assuming a constant ISRF isn't really a good reflection of reality. And then what's more, if you look at the most dense regions of the cube, which correspond to the locations of molecular clouds, even here we have like an order of magnitude variation, which might not be intuitive. You might assume that inside denser clouds, the radiation field would look very similar. So this will be an interesting area to explore. Most of my background is looking at ionized metals in UV spectra. And so one application that I'm personally interested in for LightCube is looking at how gas ionization state is correlates with the ISRF. So these are two different spectra from past work that I've done in sight lines in two directions on the sky. So these blue absorption features are showing lower ions, and the red absorption features are showing higher ions. And you can see that in these two different sight lines, the ratio between the low and high ions is different. And so naively, you might expect that higher radiation field, you'll have stronger absorption features for these high ions. But we don't actually know if that's the case. We haven't been able to measure the ISRF in a particular location before. And so I want to take a look and see if indeed these things are correlated, because if they're not, then that's likely an indication that the gas we're looking at was collisionally ionized at a higher temperature and is now cooling. So this can shed some light on the multi-phase nature of diffuse gas in the ISM, and tell us something about where the gas is photoionized or collisionally ionized, where there isn't a lot of consensus right now. I don't expect you to read all this, but these are just a few things that people have talked to me about using LightCube for, everything from magnetic fields to planet formation and dust and simulations of gas flows. And this is a data product that we're building for the community. And so we're interested in how people in the community want to use it. And so if you think that you might use LightCube, I'd love to chat with you sometime this week and hear more about what you'd like to do with it, because that's going to influence the decisions we make as we release this data product. So with that, I'll just let the movie play, and happy to take questions.
Thank you, Hannah. Jeff, why don't you go ahead?
Yeah, great work. There is now Lyman Alpha data becoming available from Voyager and New Horizons spacecraft, and Lyman Alpha being much brighter usually than the continuum UV radiation. Are you going to include that in your future light clear work?
So I think this is something that other folks are working on right now, which will be complementary to LightCube.
Sorry, great talk. Do you expect to have a lot of improvement on your 3D maps with future UV facilities? Something like data that's not from the 70s, basically.
Yeah. So, I mean, I'm hoping that the UV Explorer, which will hopefully launch in the 2030, I think that will likely would give us an on these data. It's, yeah, fingers crossed. It definitely has been a challenge with this older data. There aren't even a lot of people around anymore who can who know how the data were processed. So I think that would definitely, improve our maps for sure.
I was wondering if you considered reconstructing the radiation field in the past, incorporating stellar evolution and dynamics and things.
I haven't. That would be an interesting thing to do. I'd have to think about it. Sounds like a complex.
Complicated.
Yeah. But that would be very cool if you could get, the radiation field over time, because, obviously in the UV things are changing temporally as well. So
I'm really focused on the closest. So the motion of these stars and the proximity to the various planets makes a big impact.
For sure.
Okay. Just to note that Hollenbach and I think Padovano back like 20 years ago used the A-star locations to try to get a time variable history at a single point, showing that there was as much time variation as spatial variation. And it would be very interesting if that sort of perspective could be combined.
Yeah.
Well,
I'm very impressed by your work. Do you have plans to extend it to extreme UV and X-ray? Because for the ionization of the ISM, it's very important to go there.
Yes, yeah. So I don't currently have plans to go to X-ray. I think, not sure if we would have the data to do that. If you go to farther in the UV, you hit the Lyman limit. So the UV light's mostly absorbed, and so you don't have to worry about this much.
Yeah, although just to add, Bob Benjamin, are you speaking about?
I'll talk about that right after lunch.
Yeah. So there's a complementary project that's working on only extreme UV. So this is all far UV. But hopefully we'll merge these at some point farther. Did you have a question?
Yeah, how much you have to assume about the dust light interactions. So, for example, RV changes the absorption probability for different wavelengths.
Yes, so we do have to assume an extinction curve for the dust, to assume albedo and forward scattering angle and all of that. So it's definitely a knob that we could tweak because of the computational expense of building the cube. It's kind of challenging, but yes, that is something that we have to assume when we build the cube.
At the risk of stating the obvious, the thing you showed at the beginning, the thing we're showing now, are obviously things we're going to take a look at the intersection of. Once the UV radiation field at the edges of clouds where RV varies in different ways, this is the first thing to do.
Hack day.
What? Yeah.
Hack day.
Right. We can definitely do a first order hack day.
As an experimental astronomer who just uses galaxy data and assumes that it's the ISRF and pixel scales and kiloparsec is terrifying, it's very wrong. But to make me feel better, over what distance does the ISRF forget about a bright clump of UV stars over here? Because it seems like once you slice through away from like Orion, it kind of goes back to a baseline fairly quickly. Like over what scales is this uncorrelated? I suppose is my question.
Yeah, so I mean, obviously it depends, right, how bright your clump is and what the dust looks like around that clump. So I think it can differ. Generally, these brighter star-forming regions, you can see within like probably 100 or 200 parsecs, they stop dominating the ISRF. So it's really in the midplane where you have a lot of this variation where these brighter star-forming regions are. But it definitely does vary depending on the local conditions.
So I'm really impressed by the three-dimensional resolution of the model, and I wonder if you've looked at all at the spatial power spectrum of the ISRF, because we're seeing some simulations now, galaxy simulations, that are including dust and can, sort of do something similar. And so comparing the spatial power spectra might allow you to determine if they are comparable in, the size and the spatial distribution of the features.
Have not done that, but that's an interesting idea. Yeah.
Any more questions from the audience? Please.
Hi. I was wondering if there's scope to make more detailed map of radiation field within star-forming regions, because there we have more UV fluxes, and also radiation field can affect dispersal, which can affect planet formation as well.
Sorry, I don't think I caught this.
Sorry, I was wondering if there's scope for having more detailed map of radiation field within star-forming regions, because there we have UV fluxes, and the radiation field can affect planet formation timescales.
So you're asking if we have more
Could it be done in a, zoomed in on one?
If we can zoom in the star-forming regions.
Yeah, I mean, I think we're pretty limited by the resolution of our dust maps here, which is at best about a scale of 1 parsec. So, and in the more dense regions too, right? These dust maps can only be made if you can actually see the stars through the dust, and so in the denser regions, it's going to be very difficult to use this technique to map the ISRF.
Anybody else? Anybody on the outlines? Yeah. All right, let's thank our speaker. Our poster flash session now. I will give you the reins.
Yeah, you got it.
The reins.
Okay, everyone. I would like to first introduce Steve Wave.
Hello.
Steve is our poster guy. So the way that posters are going to work is we have our lovely poster flash sessions, and those will be occurring before each of our breaks. So you can do a quick 1 minute, 1 slide advertisement for your poster in the flash, and then during the break is your poster session. So the e-posters are going to be in the cafe with where the coffee is. Feel free to just walk up to where your poster is. Steve should have set it beforehand, so you just go to where your poster is. And then the physical posters are here in the auditorium. You can see them lined up on the walls right here. While we have the poster flash sessions, we're just going to ask everyone in this session to come on down so you can give your flash. And you can come on down now. Don't be shy. And you guys can just line up in order. And Steve, you can just open up the... We are also going to have a rolling e-poster board in the cafeteria. I'm not sure if it's up just yet, but there is, yes, Joel's giving me a thumbs up, thank you. So the big poster screen, when you first walk in on the right, is just a free floating screen. So if you're having a conversation and you're like, oh, actually, I show this in my poster, then you can just throw up your poster right there and show it then. Okay, any questions? Awesome, and Steve, you can take it away.
All right, 1 minute. I'm going to be pretty strict.
Yeah, we have 10 minutes.
All right, we have some buffer. I'm still going to be strict. All right, so first up, we have Xiyang Zhang. Yeah, come on up.
Hello, I'm Xiang Zhang from Max Planck Institute for Astronomy, MPIA. And in the Greg's talk, the first talk, he has shown you a result of mapping dust RV in the Milky Way, as you can show here and here. Beyond just mapping them, we have proposed a theory that explains the anti-correlation between RV and dust column density, or in Greg's words, the U-shaped curve. We propose that it is PAHs that the growth of PAHs that strengthen the 2175 feature, which contributes to B band much more than V band, and therefore decreases RV. If you're interested in more details, come find me and at my poster. It's number 4 with a purple background. Thank you. All right. All right, go ahead.
Hi everyone, I'm Sapna Mishra. I'm postdoc at SCSCI. As we all know, Magellanic Stream is the largest gaseous structure on the sky, formed due to the interaction between the Milky Way and Magellanic Clouds. However, distance to the gas of the Magellanic Stream is not known. So in this work, we have used very simple and direct method to measure this distance. We have used 5 blue horizontal branch stars with known distances, and they're passing through stream, and then we observe them using VLT-UVS. And the idea is really very straightforward. If you see an absorption in the spectrum of a star at the stream velocity, the stream has to be in front of that star. And if not, that stream is behind that star. And as you can see, in none of our stars, we have seen absorption at the location of the stream. So from that, we concluded that stream is at least 50 kpc away from the sun. This is the first observational constraint on the stream distance, and it will be a really crucial input for the dynamical modeling of the Milky Way and LMC system. If you want to know more about it, please find me and please visit my e-poster. Thank you.
All right, now we have Nick Indriolo.
Hi all, I'm Nick Indriolo here at Space Telescope Science Institute.
And I study cosmic rays and the cosmic ray ionization rate. So we use interstellar chemistry, specifically of the molecule H3+, to determine cosmic ray ionization rates in the molecular ISM. Once you get into molecular gas, you need cosmic rays because the photoionization does not operate there, right? So we're using basically the Gaia dust and gas maps to try and start mapping the cosmic ray flux in these various clouds. So you can pinpoint where the H3+ absorption is happening and get an ionization rate in these various gas structures. Now, when I say map, we've got like 12 data points because these are difficult observations. It's like 1% deep using high resolution spectra. But you can see here, we are starting to get kind of a map of the ionization rate that correlates with the dust features, and we see different regional ionization rates. So one cloud is a bit higher, one cloud is a bit lower, and we're trying to figure out what exactly that might mean for cosmic ray sources and particle propagation. So if you'd like to know more, come find me at the poster.
All right, now we have Asmain Nisak.
Hi, everyone. My name is Asmain Nisak. I'm a postdoctoral research associate working at Wesleyan University with Seth Redfield. And I invite all of you to check out our exciting poster exploring the hypothesis that Earth may have passed through a cold, dense gas cloud 2 to 3 million years ago. And this time is interesting because there is a peaking in extraterrestrial radioisotopes, a transition from forests to savannas, and the emergence of humans. And this may be due to supernovae that have produced galactic cosmic rays recently, within the past 10 million years. How exactly these isotopes were deposited on our solar system, though, is not very well understood. So Ofra et al. 2024 suggests that it may be the case that Earth may have passed through a cold gas cloud, compressing the heliosphere and exposing the Earth to galactic cosmic rays. However, this interesting idea relies upon distance assumptions. So what we are doing in our poster is that we are constraining the distances to the cold, dense clouds that the Earth may have passed through. And if you want to know more, feel free to come check out our e-poster in the cafe. Thank you.
And lastly, we have Monique Aller.
So we are studying the interstellar medium and circumgalactic medium in distant galaxies out to a redshift of 2 using not background stars, but background AGN that are in physically unrelated, even more distant background galaxies. My poster focuses on the silicate dust feature, in particular the 10-micron silicate dust feature, in which we see a large degree of variation from system to system in the structure, as well as differences relative to the Milky Way. These are indicative of composition differences and grain structure differences. We can also look at the properties of our silicate dust grains in relation to other dust properties, such as the extinction, and relative to grain properties. And again, we find differences relative to the Milky Way diffuse interstellar medium. Thank you.
All right, that concludes our first poster flash talk session.
Awesome. Okay, well, we are now in our morning break.
So you all can go into the cafe, have some coffee and light refreshments, and remember to write discussion ideas on the whiteboard in the cafe. And those wonderful talks earlier this session. Curiosity. Oh yes, we will be back. What time is it? We will be back at 11:10. We have a half an hour.